today I want to talk to you about the mathematics of bell ringing. Bells, of course, have huge cultural significance across the world. In our lives, bells ring out in celebration or in mourning or to mark the passing of time. In Britain, we have the chimes of Big Ben to herald the new year. And of course, in school playgrounds, the handbell telling you when to go in to class has been there for hundreds of years. We're going to discuss some of the mathematics around bells and bell ringing, and today we'll look at such questions as why are bells bell-shaped? And what mathematical bell ringing conundrum took 300 years to solve? We'll also come across some curiosities, like the bell so big it was actually used as a chapel. So today, the main focus, I guess, of my talk is going to be the British style of bell ringing called change ringing. And probably within Britain, it's most popular within England, but the other countries as well have this tradition. So the kind of setup is that you have your church and with a bell tower and several bells in it, and you want to ring your bells and make a pleasing sound. Of course, bells are very heavy instruments. We can't just do whatever we like with them. Once you set your bell swinging, it's going to want to carry on swinging. So when you're playing bells, you might have a series of bells. We normally number them from the highest to the lowest. So 1 is the highest, the treble, and then you go down to the very lowest one, which is called the tenor bell. And you can, of course, as we're mathematicians, we call them 1, 2, up to n. The ringers will then play rows, and a row is each one of the bells played exactly once. And if you're going to play a sequence of rows like this, that'll be a change ringing performance. Each row must contain each bell ringing exactly once because, as I say, once the bells get started, it's quite difficult to stop them. So there are various things you could do, various rows you could play. And our first question would be, how many different rows can you play if you have n bells? Let's say 8 bells. So I've shown on the slide some examples of possible rows with 8 bells, which is a fairly typical number to have in a parish church. So if you play the bells from highest to lowest in order, that's called rounds. So I've shown an example for 8 bells, but da-da-da-da-da-da-da, that would be rounds. And you might do something different. You might do what's called queens, apparently because Queen Elizabeth I liked it. Da-da-da-da-da-da-da-da. And then other possibilities are possible. I've written a couple of them down on the slide, Tittums and Whittingtons, which ends with turn again Whittington, that's why. There are various other possibilities. But how many possibilities? So that's our first question, just to get us started. How many different arrangements are there of n bells? So let's start with a small n. That's what we do in mathematics. We don't know the general answer. Let's start with a small example. Let's start with 2 bells. So you have bell 1 and bell 2. Bell 1 is the higher one, bell 2 is the lower one. Well, obviously, you can either play bell 1 first, then bell 2, or 2, then 1. So 1, 2, or 2, 1. That's the 2 possibilities. Every time you add a bell, you get more choice. So if you go up to 3 bells, think which bell's going to go first. It could be either bell 1, bell 2, or bell 3. So you've got 3 choices for what goes first. And once you've determined that, you've got your 2 remaining bells, and we know that there are 2 ways to play a set of 2 bells. So that's for 3 bells. And I've highlighted on the slide the first number. Once you chose the first number, there are 3 ways to do that. Then the other 2, there are 2 choices for the next one, and 1 for the final one. So that gives you 3 times 2 times 1, which is 6 possible rows that you could play. For 4 bells, it's the same kind of thing. So you've got to put your 4 bells in some order. So you've got 4 choices for what goes first, then 3 choices for the next one, because you've used your first bell already, and then 2 choices and then 1. So the total number is going to be 4 times 3 times 2 times 1, which is 24. And mathematically, there's a notation for that calculation. So for the general case for n, if you have n bells, then the total number of possible rows that you can play is n choices for what goes first, then n minus 1, n minus 2, and so on. Multiply all these together, and you get some number. And that number is called n factorial. So the factorial notation is this exclamation mark, or I did know someone used to call it bang for exclamation mark. So that's this notation. You just multiply all the numbers up to n. Now, this function, this factorial function, grows very, very quickly. We have all heard a lot about exponential growth and how fast that is. Factorials are even faster growing than that. So it grows very quickly. Now, I'm going to give you a table on the next slide with lots and lots of numbers in. We don't have to learn and absorb all of them, but I just want to give you an indication of how fast this function is growing. And just one little word which isn't absolutely rigorously defined at the moment, but we'll get to that. So if you're going to ring all possible rows, doing that is called an extent, and you play each one exactly once, roughly speaking. There are some constraints, and we'll get to those. So let me show you a big table with lots of information in it, but as I say, I don't want you to absorb all of it. I just want to show you the columns are, so the first column is how many bells you've got, then the name for ringing that many bells. We'll discuss why those names later on. Then the third column gives you the number of possible rows that there are. So this is your factorial function. And then the final column is telling you if each row takes 2 seconds to ring, which is about what it takes, then how long would it take to do a complete set of one of each row and extent. So as we've seen, for 3 bells, the answer is 6. For 4 bells, the answer is 24 rows. So that's how many rows there are. And so then you double that up for the number of seconds. Now, you might think, if you weren't looking at this table, well, if 4 bells requires 24 rows, then 8 bells, maybe it's 48, or maybe it's some, you might make a guess. And actually, if you look at the answer for 8 bells, which I'm pointing to now, it's 40,320, right? That's how many different permutations there are of 8 bells. And that would take nearly a full 24 hours, 22 hours and 48 minutes. So that's a lot. And it gets worse if you double it again to 16, and there are just 2 or 3 places in the world that have a ring of 16 bells. One's in Birmingham. Then you're looking at over 1 million years to do that. Now, we'd have to be quite energetic to want to do that. But just looking even at the column with the different numbers of the factorials, you can see just by the way the numbers are growing bigger, this is a very fast-growing function. So we are not probably going to stand there and try and ring an extent on 10 or 11 or 12 bells. But what we can do is ring smaller numbers of different rows, and if you do 5,000 different rows, that's called a peal. So we'll talk about those a little bit as well. I couldn't resist putting the number 4 if you had 19 bells. The reason is that this is the maximum theoretically possible we could achieve if we started right the second this lecture finished and we didn't have a break and stop at all for anything, then it would take us 7.7 billion years to do it, which is about the length of time that scientists estimate it will take before the sun explodes into a red giant and engulfs the Earth. So, we can do it, but we have to focus and put our minds to it. So, all right, we can talk about how many different rows there are and this idea of an extent. But there's more to it than that. The physical setup of bells, these great big heavy things, means we don't have entirely free choice about which order we play the rows in. And to shed some light on this, we need to learn a little bit more about bells and bell ringing and the development of those things. So let's just talk about the shape of bells. So, of course, back in the dawn of time, at some point somebody realised if you get a bit of metal and you bang it with something, it makes a nice loud noise. Now that could develop into things like gongs, which are pretty much flat. But the other thing you can do is realise after a while, actually, if you bend over your piece of metal, then and perhaps join it together, then you get a much more resonant, powerful sound. And this is the origin of bells. Now, what metal should you use for your bell? Well, it's got to be strong enough to withstand the repeated hitting from the clapper or the hammer. But if it's too rigid, you will get a very flat sound and you won't get the nice resonances that you would like if it can vibrate a little bit. So after some time, it was found that bronze is the best metal. It's an alloy of copper and tin on their own are too soft, but bronze is just right. Now, what about the shape? We've got this characteristic bell shape. Well, the shape you make your bell depends on the use you're going to put it to. So there are 3 examples of bells on the next slide. On the left, you've got a cowbell. Now, a cowbell does not have to be tuned to a particular pitch. You don't want it to cost a lot of money. It doesn't have to carry the sound for 14 miles or anything. You just want a cheap and cheerful thing. So, of course, that gives you that shape of it's not particularly uniform, but it's good enough and doesn't cost very much. On the other hand, if you want a precise pitch, then something like the tubular bells in an orchestra, that's a very important thing. You want a nice pure tone. So that cylindrical shape, the circular cross-section, gives you both strength and it allows the sound waves to move smoothly around the perimeter. At a constant perimeter, you'll get constant frequency and pitch all the way up and down. So that's why you might choose that cylindrical shape. Now, our church bells have a different shape again. They still have a circular cross-section. There are several reasons for that. Let's look at the church bell a bit more clearly. So the circular cross-section, it's for strength, it's to allow the sound waves to travel smoothly, but also it's to do with the manufacture. So when you're casting bells, the way you get the shape of the bell is you get a sort of vertical cross-sectional piece called a strickle, and you rotate it around to refine the shape and make the final shape. And of course, that circular rotation will naturally lead to a circular cross-section. So that's why circular cross-section, but of course in bells we have this variation in the diameter or circumference up and down. And there are some reasons for that. So one is that a bell is actually, it's almost playing a chord all on its own, because the frequency of a pitch, and you'll know this if you watched my previous lecture about the mathematics of sound, and if you didn't, you can go and watch it on YouTube. The frequency of the sound produced is inversely proportional to the length, in this case to the perimeter or circumference of the circle at that point on the cross-section of the bell. So by going from smaller to larger, you get a range of different frequencies. And the shape of the bell, the particular shape, has evolved over time to produce frequencies that sound harmonious together. And that means that comes from the frequencies being in nice, small fraction or ratios to each other. Why is it wider at the bottom and not at the top? Well, if you think about where bells are, the shape of getting wider at the bottom, you see this in a lot of other instances, like the brass instruments in orchestra, trumpets, euphoniums, that kind of thing. But also in things like megaphones, that actually is the best sort of shape to get the standing waves from inside the instrument out of the instrument. So it helps to spread the sound. But if you have a bell hanging up high in a belfry in your village at the top of the steeple, and it's swinging backwards and forwards, the wide bottom part, the mouth of the bell, is going to be pointing downwards, not upwards, and so people are going to be able to hear the sound more easily. So that's where we get the shape of the bell. Now, the particular exact tunings of those pitches was, I won't say finalised, but a standard tuning was arrived at in the 19th century due to Arthur Simpson, and the Simpson tuning is named for him. So it controls 5 partial frequencies, different frequencies that are played by the bell. So the note we hear, and that's called the strike note, relative to that note, which I've written as having a frequency of F, say, there are these 5 frequencies. You've got the nominal, the tierce, quint, prime, and hum. So just as an example, the quint, which sounds like it ought to have something to do with 5 from that word, indeed so, it's a perfect fifth above the strike note that we hear. The tierce is a minor third above, and so on. So these small ratios of frequencies are ones that sound pleasing together. Curiously enough, so this prime note is about the frequency that we hear, but even if it isn't, even if the bell isn't tuned like that, it's curious, but we do hear that still that note, that frequency F. And the reason is it's something called a phenomenon of virtual pitch. When we are hearing lots of things that are themselves overtones or harmonics of a particular pitch, even if that pitch is not played, our brain sort of reconstructs it. So it's like a phantom thing that we reconstruct that isn't actually there, almost like an auditory illusion. So our brain sort of constructs this frequency, and we hear it even if that prime is not tuned in that way. So the shape of the bell is determined to get these 5 frequencies. And of course, it's more complicated than that, because in a ring of bells, a whole set of bells, you want them to be in tune with themselves, but also with each other. So it's a really complicated process. The way they are tuned, bells, once they're cast, there's not much you can do. A great big lump of bronze. The only thing you can do is to chip away little bits of the inside of the bell. So in a process, it used to be this process called chip tuning, and you can see a bell maker, he's getting some instructions from the guy with the violin in this picture on exactly what he needs to do at various parts of the bell. Nowadays, vertical lathes are used, and that gives a more even smoothing out. That can only increase just very slightly the diameter of the point in question, and so it can only lower the frequency a little bit. So, there's not much scope. You better get it right, really, almost right, when you cast it. Now, there used to be about 60 bell foundries in Britain at the heyday of bell ringing, I guess. Well, it's still in its heyday. But now, for most of the last century, there were only 2, which was the Whitechapel Bell Foundry, which is like the oldest business in England. It was founded in about 1570, I think. And then the John Taylor Bell Foundry in Loughborough. Very sadly, the Whitechapel Bell Foundry, which should be saved somehow for the nation, it had to close a few years ago. But there is a campaign to preserve some of that historical knowledge and bring that back if we can. So I'd urge you to go and find out about that. John Taylor is still going in Loughborough. It's the largest bell foundry in the world. So that's what we do to tune bells. It's a very complicated process, and you can only tune them a little bit. But that's why the bells are those shape. Now, I just wanted to, in passing, mention a few important or very large bells, just for interest. So the bell on the left in the picture, this one here, as you can see, it's massive. This is the Tsar bell, and it's on display in the Kremlin. It's the largest bell in the world. It's 202 tons, that's quite big. Now, this is perhaps, is it a bell if it's never been rung? It's a philosophical question. Perhaps it's better to say it's the world's largest bell-shaped thing. But, it's a bell. Let's say it's a bell. This bell was made hundreds of years ago, and it was actually damaged in a fire after it was made, and part of it broke away. It's not shown in the picture, but you can find pictures online where that's shown. So what were they going to do with it? Well, for a while it was used as a chapel. So it's weird to think you could have a bell in a chapel, but you can also have a chapel in a bell. And the door to the chapel was this broken off bit. So that's a massive bell, never been rung, don't know if it counts. One that definitely is rung, the largest working bell in the world, is the Bell of Good Luck in China, Hunan in China, and that's 116 tons. And if you get the transcript of this lecture, I've put a link at the end to a video of someone actually ringing this. If you go there, you can actually pay to ring it, and it's really quite an impressive sound that it makes. You have to take a run up with this giant hammer and hit it with all your might. Well, the largest bell in the UK, coming a bit down to reality, is this one here, the right-hand bell on the slide. That you can go and see. It's the Olympic bell, and that was designed by the Whitechapel Bell Foundry. It weighs 23 tons, which is respectable. It was rung in the Olympic Games in 2012. You can go and see it now in the Olympic Park in London. And although it isn't rung anymore, apparently it would be too loud and it would disturb the neighbours. Well, maybe they should let them ring it just once or twice a year. But that's there. If you want to look at church bells, the largest church bell in the UK is Great Paul at St Paul's Cathedral. That's not part of a ring, but it does ring out on special occasions. And then there are, many other good bells and rings of bells around the UK. As I said, I think the one with the most bells is in Birmingham, but someone may perhaps correct me on that, 16 bells. Normally, it's between 8 and 12 bells that you have. So in your local parish church, if they have bells, you might have 8 or 9 bells. Okay, so there's some interesting bells. One thing that makes British or English bell ringing different from what is happening in the rest of the world is that, in other countries, perhaps they might have lots and lots of fixed bells, which they ring with clappers. They might have bells that just swing backwards and forwards, but they don't have what we have, but developed in England and in the UK, which is what's called full circle ringing. So bell ringing has a venerable history in England and Britain more widely. And part of that reason might be that in 750 AD, a decree went out that a Saxon could become a thane, so like almost a prince, if he had 500 acres of land at least and a church with a bell tower. So of course then everyone wanted a bell tower in their church, and gradually over time you might start to add more than one bell into your church tower, because they could signify different things, like one bell might mean it's time to go to church, another one might mean there's an emergency, and so on. So there started to be more than one bell, and eventually several bells in church towers regularly. By Tudor times, this was common enough that at times of celebration, people started to think, well, we'd like to make a pleasing sound with our bells, and maybe sort of ring them in pretty patterns and things. How can we do that? What are the possibilities? We've already seen for 4 bells, there are 24 different rows you can make. Can I play all the rows? What do I do? Now, there are constraints, as I've said. There is not just total free choice about you play one row and then you can play anything else, because these bells are great big heavy things. And so originally you would have had big bell, lever, rope hanging down, you pull on the rope, the bell starts swinging, and you've got no control then at that point. There's not much you can do. On the downswing, it's just going to come down. So then you can give it another tug maybe, but when it's coming down, you have no control over the speed. It's just going to do what it's going to do. The big innovation was the gradual development, when you see the finishing stage of it on the picture, which is, so instead of a lever, there started to be a quarter wheel. That gives you a tiny bit more, and the rope is going on the wheel. And then it changed to a half wheel, and eventually a full wheel, with the rope able to move on both sides. And that means the bell is going round in a full circle, so full circle ringing. When that happens, if you think about what happens when a large, heavy object is rotating in a circle, it picks up speed at the bottom and it slows down at the top. And at the top, it's almost still. And it just goes, and then slows down and then comes down again. So at that top point, you've just got a moment of slightly more control. You can just tweak the speed a little bit, you can just hold it there for a second, or you can bring it round faster, and that allows you just a bit of latitude to say we're going to change the order a little bit. What you can do is you can change the order just of adjacent pairs of bells in the ordering. So one bell that went second one time, it could go third the next time, it could swap with its neighbour. So this is why we start to be able to try to perform extents or different rows, but we have this really strong constraint, and that's where it starts to get a bit mathematical. I couldn't resist including this little quote about change ringing. So Dorothy L. Sayers, writer of detective fiction and other things, and this is from one of her Peter Wimsey novels. So as you can see from the picture, very gruesome things are happening in the belfry. This book is called The Nine Tailors, which itself is a bell ringing reference. Her father was a bell ringer, and she knew quite a lot about it. And if you read that book, you will see there's a lot of bell ringing terminology which you need to be aware of to even sort of understand some of the words that are used. But she has this little quote, which, okay, we forgive the slight xenophobia perhaps, but she says the art of change ringing is peculiar to the English, and like most English peculiarities, unintelligible to the rest of the world. Well, we hope to make it intelligible. To the musical Belgian, for example, it appears that the proper thing to do with a carefully tuned ring of bells is to play a tune on it. Why not? By the English campanologist, the playing of tunes is considered to be a childish game, only fit for foreigners. The proper use of bells is to work out mathematical permutations and combinations. So, of course, here, I'm a mathematician, we're going to work out some of these permutations and combinations. So, here are the rules of engagement. We've already said the bells are numbered from 1 up to n, highest to lowest, so n would be the tenor bell. They sound in a sequence of rows. In each row, each bell plays exactly once in each row. Between the rows, the movement between your rows is called a change. So we want the recipes for what changes are allowed. Okay, each bell sounds once in each row, we've just said. Now, each bell can move at most one position in each change. So a bell could swap order with the one exactly before it or after it, but nothing more than that. So you can do these little swaps of adjacent bells, or the bell can stay where it is, but that's it. So you can't just do anything, it's not open season. So some examples, if you have 4 bells, so you could start with, here are the bells 1, 2, 3, and 4, and we're going to start with rounds, let's say. So you always start with rounds, 1, 2, 3, 4, all the way down. Put the bells in the correct order. When I say the order, we're not physically moving the bells, I mean chronological order. Okay, it's tempting to use a positional allegory for this, but it's always chronological order. So you could start with 1, 2, 3, and then 4, just play them in that order. Then you could do a plain change. That means just swapping one pair. So you could swap the 1 and the 2 over, and it becomes 2, 1. 3, 4. Then you could get a bit more racy and do a cross peel. That's where you're swapping more than one pair. So in this case, you will swap, you've got your 2, 1, you're going to swap them over back again and do 1, 2, and the 3 and the 4 swap as well, and that becomes 4, 3. And then, finally, you could go back to rounds if you wanted by swapping that last pair. Something you're not allowed to do, just as an example, illegal, you cannot do this in bell ringing. You can't play rounds 1, 2, 3, 4, and then immediately follow that with 4, 3, 2, 1, because the 4 and the 1 are moving too far. That big, heavy 4 tenor bell played last in one row. It can't then immediately speed up so much that it plays first in the next row. Okay, so that would be illegal. So with those rules, then, it's not at all clear that we can play every row exactly once, one after the other, because it's not clear that we are able to get between them using these legal changes. And even if we can, it's not clear we can do it without repetition. So, just to remind you, an extent, then we can define it properly on n bells. Starts and ends with rounds, 1, 2, 3 up to n. The ending rounds, that's just to finish off. That's like the final flourish. But apart from that, every single possible row must be played exactly once. You can't miss any out, you can't repeat any. So a full extent on n bells will have n factorial rows, as we've seen, and then you just add that final rounds onto the end. And a peal, as I've said, is over 5,000 different rows, and that starts to come into play when you've got more than about 7 bells. So 8 bells, you need 40,000 different rows to form an extent, and obviously you're not going to have time for that on a Sunday morning. Okay, let's look at 3 bells then, and think what's possible. So, we've got our numbered bells, 1, 2, 3. If we're numbering the bells, we don't also want to number the positions of the bells because that's going to be confusing. So we label those with letters. So the kind of initial, the first position, which one goes first in any row, that'll be A, and then B, then C, and so on. So we use letters for those. As we've seen, you're never going to be really in practice playing more than 19 bells, so unless you move to a different planet. So letters ought to be fine. Okay, so you've got your positions A, B, and C. Now, 3 bells. What can you do with those 3 bells? You can only swap adjacent bells. So the bells in, that's A, that's B, that's C, the bells in position A and B could swap there next to each other chronologically. And then the other one in position C would have to stay where it is. It's got no one to swap with. So that's one possibility. And I've written that on the slide as A, B in brackets. That means the bells in positions A and B swap over. The other possibility, so you could do A and B, the other one is that you could swap B and C, the bells in position B and C, over. They're next to each other. But you can't swap the bells in positions A and C. So there are 2, and only 2, legal changes for 3 bells. You can either do AB or you can do BC. If you do AB, and then you do AB again immediately, you'll get back to something you just had. So another thing is, we can't do either of these things twice in a row. So really the only way, the only hope for an extent on 3 bells is that we alternate these 2 possible things, and then there's just one choice, which one goes first. You can see then on the slide, there are 2 columns here that are showing what happens. And you've got the positions A, B, and C, and then the bells themselves, we start with rounds 1, 2, 3. And then these little crossings, that's just to show you visually which ones are swapping over. So if I do AB, I swap the ones in position A and B, and we get 2, 1, 1, 2 swaps over. Then we do BC, and we just alternate like this. And happily, everything works out. We get 6 different rows, and then we do the next move takes us back to rounds. So that is an extent. In the other column, we see the same thing happening, except it's slightly different because we're starting with BC, but you still get 6 different rows, which is 3 factorial, and then rounds. So that's good. So we can do extents on 3 bells. What about more than that? Is an extent on n bells always possible? Well, let's see. There is a technique we can use for higher numbers of bells, as long as it's an even number. So on the slide, I'm showing this method for 4 bells. It's called plain hunting, and I'm told that this is because the bell number 1, the treble, hunts through the others and then back again. I'm not quite sure. It doesn't look like hunt. Anyway, that's what it's called, and that is apparently why. So what's happening here is you've got, again, alternating things. You've got 2 swaps going on across peal, and then you alternate that with swapping the middle 2 bells. And you just repeat that and come back. So explicitly speaking, what's going on, you can do this with an even number of bells. So if n, the number of bells, is even, so it's twice some whole number k, you can do this method. Or you can do it if you are following the common principle that you leave the tenor bell always playing last. And that's kind of like a musical punctuation. It lets you know, oh, that's a row, this is a row, this is a row. Every row ends with the same thing. So it's like finishing a line and starting the new one. So if you are doing that, and then we say the tenor bell is covering, it's just sitting in that one place. If you do that, then it's kind of out of the equation, and it's the n-1 bells are moving around. So if you've got an odd number of bells, but the tenor is covering, so really you're moving an even number, then you could do this method in that case as well. But let's ignore any covering tenors for the moment and just focus on the 2k bells that are moving. So we've got these 2 changes that we're going to just alternate with each other. And if you've got twice k, 2k bells, then they split into k, exactly k pairs, and nobody's left on their own, of adjacent bells that can swap. So you see it with 4 happening there, the first 2 and the last 2. So bell A and B can swap, bell C and D can swap. Then the other change, so that we call that R, the other one S, is going to be, well, you leave the bell in position A and the bell in the final position, you just leave them there, and you do the swaps on just the middle 2k minus 2 bells. So you've got k minus 1 swaps. And you can see that happening with 4, so we leave bells in A and D fixed, and we swap over the B and C bells. So just to see that written down, on 6 bells, the positions are A, B, C, D, E, F. So R would be swap A and B, swap C and D, swap E and F. And S would be leave A and F where they are and swap B and C, D and E. On 4 bells, you can see we've got bells in positions A, B, C, D, and we swap A, B, C, D. And then change S would be leave A in the position A and D where they are and swap B and C in the middle. Okay, so you can see that happening for 4 bells in the slide. Now, if you do this, after 8 rows, starting with rounds, the next thing you do is it's your turn to do S, and you get back to rounds. So this is not an extent on 4 bells. Never fear, we're going to turn it into one. It's not yet an extent on 8 bells, on 4 bells, because there are 24 different rows for 4 bells, 4 factorial, 4 times 3 times 2 times 1. And we've only got 8, and then the final rounds. So we have to do something, we have to tweak this. And this leads to a method. And the method for an extent on 4 bells, or one of the methods, is called plain bob minimus. We'll explain that terminology in a second, at least a little bit. So what you see in the slide are 3 columns. The first column is the plain hunting, starting with rounds. And if you remember that previous slide, when we got to the end of the plain hunting, our last step would have been S, so swapping the middle pair, and it would get us back to the thing at the top of the column, rounds. We don't want to do that because we want different rows. So instead of that final S to take us back, we do, I guess it's CD. We swap the bells in positions C and D. So we've got a 2-4 here. We do that swap, and at the start of the next column, that 2-4 has become a 4-2. We've now got a different starting point for our hunting. So we do plain hunting again. And at the last stage, we would be expecting to do our S, our middle swap next, but we don't do that because that would get us to the top of the column again, and we'd be going round in a loop. So again, we do this CD, this swap of the last 2 things. And that takes us to some new starting point, and then we do plain hunting again, and we finish up with 1, 2, 4, 3, and we can get back to rounds after that by just, again, doing that CD, that swap of the final 2 things. 1, 2, 3, 4, rounds. This, I mean, you can check if you like, but these do comprise 24 different rows as needed for an extent, all with legal changes between them, and then we finish the next row is rounds. So that is an extent on 4 bells. And we've made it by taking 3 lots of plain hunting and putting them together with just one other thing in between. So this is kind of a good thing in terms of learning how to do it. And there are hundreds, thousands probably, of change ringing methods. Plain bob minimus is just one of them. The ringers will follow a set pattern that they have learnt, and then a call will tell ringers what to do to switch to the next method. So you do plain hunting, then you do your CD, then you do plain hunting again, and so on. Now, there are different names for change ringing methods, and I just wanted to show you some of these because I think it's one of the loveliest things about bell ringing is these just wonderful names for the change ringing methods. So each method is named, it's got an initial part, which is, what the composer decides to call it, but then the end part, the last word, is telling you how many bells are involved. So 3, 5, 7, 9, 11 bells, odd numbers of bells, are labelled in order, singles, doubles, triples, and so on. And then even numbers of bells, 4, 6, 8, 10, 12, and so on, are labelled minimus, minor, major, royal, maximus. After that, you just revert to 14s and things, because we don't really, when this terminology was invented, no one really had 14 bells. So why have we got this thing? Why have we got triples for 7? Well, it's because of the convention of having the tenor covering. So if you imagine having, say, 6 bells, The tenor is covering, so he's out of things. There are 5 remaining bells. What's the most number of swaps you can do on 5 bells? Well, you could have 2, but then there's always going to be one guy left on their own. So you can do 2 swaps, doubles, but you can't do a triple swap. But if you go up to 7 bells with the tenor covering, then you have 6 bells, and then you can do 3 swaps. So that's why 7 is called triples, because it's the smallest number if you have this convention of the tenor bell covering, the smallest number where you can do triple swaps. So each new odd number gives you a new and exciting type of cross peal or number of swaps you can do. So we see that, for example, plain bob minimus. Minimus tells you there are 4 bells. Stedman doubles, we'll meet Stedman in a moment. Doubles, that's 5 bells. Grand Sir triples. Triples is 7. Primrose Surprise Major, what a lovely name. That just makes you feel happy, I think, just hearing that name even. Major, okay, that's 8 bells. Avon Delight, Maximus, 12 bells. So if you see any of these, you'll be able to say how many bells are involved. Well, there are some questions we can ask mathematically. Is an extent possible on our particular number of bells? Luckily, it turns out the answer is yes. But then, once we know it's possible, can we design interesting peals, 5,000 different rings, or extents? So interesting means no bell is just sitting around doing nothing for more than one row. So, for some numbers of bells, there always has to be at least one bell fixed, for example, if you have an odd number of bells. But we don't want too many bells to just not do anything. The most interesting ones are where the bells are moving as much as possible. They're not just sitting in the same place in the ordering. So we would like to find peals or extents where no bell is in the same place for more than 2 rows. And there's a mathematical aspect to solving that. Can we design memorable methods? So you have to learn these methods. If there's structure, then it helps you to learn them. For the bell ringers, it's fewer calls that you need to do. So we want structure, but we also want the variety of having these interesting peals. And then how do we actually prove that we have a true extent or peal? So true, in bell ring context, means it really does consist of different rows. All the rows have to be different. None are missed out if you're trying to do an extent. That's a really tricky one. Even for that plain bob minimus that I showed you with 24, it's not absolutely instantly clear that all the rows are definitely different. You have to check, but human error and so on. It'd be nice to have a real a technique for checking. Now, there are all sorts of peals. If you go to a church which has bell ringing, you will find often on the walls of the church what are called peal boards, which record interesting or peals that have been rung or extents that have been rung particularly fast or in commemoration of particular events. This one, I was so delighted to find this in my local parish church, St Mary's in Walthamstow. So this is a William peal. So this says, on June the 4th, 1898, was rung a true peal. It verified, all the rows were different, of Grand Sir Caters, so Caters, that means 9 bells, 5,003 changes in 3 hours, 20 minutes. And why is it a William peal? It's because all the ringers were called William, composed by William T. Elson, conducted by William Pye, the Reverend William Langhorne, the vicar, and even both the church wardens were called William. So, okay, that's not a mathematical criterion for a peal, but there are plenty of other things. And we have to know also, how does William T. Elson compose this peal? How can we have methods? Can maths help us to get these methods? Now, bell ringing developed a lot, particularly in the 17th century. We had lots of churches with bells in them. People thought that bell ringing was a very healthy thing for a gentleman to do. So that book there, The School of Recreation, mentions ringing in its list of, hunting, racing, hawking, ringing as a sport that a gentleman would like to do. I just want to read you what it says. It says, bell ringing is highly esteemed for its excellent harmony of music it affords the ear, for its mathematical invention delighting the mind, and for the violence of its exercise bringing health to the body, causing it to transpire plentifully. And they did transpire plentifully, and they were often actually paid in beer, the ringers. There were rival teams, so sometimes inns would sponsor teams and pay them in beer. There were parish teams that, rival parishes. And then there were all these clubs and societies like the Scholars of Cheapside, the Society of College Youths, which is still going strong, actually. They've perhaps spell it slightly differently now, but they're still going. Society of Cumberland Youths. All of these were springing up and wanting to do new things with bells. Extents were achieved on 4, 5, and 6 bells in this period. Soon after, in the 18th century, there were peals that were done on higher numbers of bells. So a lot of progress was made, often, or largely due, maybe you could say, to the influence of Fabian Stedman. So he was a London printer and bell ringer. This is the memorial plaque to him at St Andrew's Undershaft in London, where he was buried. And this was put up in the 80s by the Society of College Youths. So he did two things. He was a printer, and he printed a really influential book, Tintinologia, on change ringing. But then he wrote his own book, Campanologia, or The Art of Ringing Improved, about 10 years later. And in it, he gave 53 what he called London peals of his own invention, including what we now call Stedman doubles. And crucially, he gave really, really clear explanations. It was very logical explanations of why these things were true peals. And he was illuminating the structure of these peals in a way that, although the terminology is different, we can now recognize mathematically as a sort of similar way of thinking that we now have, and that we would express in the language of the mathematical structures known as groups. So I want to just talk about groups for a few minutes. I'm a group theorist. I love groups. I see them everywhere, but they are actually here. And I mention them if you watch my first lecture on mathematics and musical composition. Groups are involved there as well. So here's another place where you see them. So just a very brief thing, and this is a bit much. It can just slide over you. You can relax for a minute or two and then come back. So a group is a set of objects. It's just some things, but there's a way of combining them. So I'll do an example just with numbers. The rule says that when you combine your objects in whatever way is given, the outcome is going to be another thing that you've got in the set. So if you take just numbers bigger than 0, just numbers bigger than 0, and how are we going to combine them? We'll combine them with multiplication. Okay? So if you multiply two positive numbers, the outcome is a positive number. So far, so good. So that means we've got this closure property. You are not escaping from the set by doing these combinations. Then there are three other things, which I'll just briefly mention. So with multiplication, if you multiply any number a by 1, you just get a back again. So you've got this number 1, which we call the identity element. That is not doing anything. It's not changing any other element in the set. So that's called the identity element. It leaves everything identically where it is. Then we have this idea of undoing. So every element, everything has an inverse. You can undo the damage you've done. So if you multiply by a, then how can you undo that and get back to what you had? We just divide by a. And you can do that if a is not a 0 number, which these are. So what's division by a? Well, that's multiplying by 1 over a. And 1 over a is also a positive real number. So you've got this undoing property, and that means that you can do things like solve equations. You can find, if you have a times x equals b, you can find x, and you can divide through by a. So that's a useful property. And then finally, we've got this associative property, which is just something about how we bracket numbers. It doesn't matter which way you bracket the things, the outcome is still the same. So I won't go into the details of this, but if we now look at the way, all possible permutations of different objects. So you could think about decks of cards and shuffling them, or you could think about bells, numbered 1 up to n, and the different permutations of them are different rearrangements, and for each one you would get a different row if you're talking about bell ringing. So the positions of the objects are A, B, C, and so on. The objects themselves we can associate with, or number them 1, 2, 3, and so on. And that set of all the permutations you can do, changes are a proper subset of that. They are examples of the kind of permutations. We call that Sn. So for example, our cross peel A, B, C, D will send 1, 2, 3, 4, 5 all the way along. It will send it to 2, 1, because you're swapping the things in the first two places, 4, 3, and then the rest stay the same. You can check that the rules hold. I'm not going to do that. But just for the closure thing, if you shuffle something and then you shuffle it again, the outcome is a third more complicated shuffle. So it's still another thing of that same type. If you just do the thing and then do another one, that's how we're combining the elements. So as I've said, permutations correspond to rows in terms of bell ringing, and there are n factorial permutations of n bells. In particular, let's take the number 4. Permutations of 4 objects. There are 4 factorial, which is 24 elements, and that corresponds to having 24 rows in our extent. So I was reading about groups, and I came across this fantastic article by former Gresham professor of geometry Robin Wilson and Arthur White about the hunting group. So we've seen plain hunting. You could make a group out of this. So not all permutations of bells are legal changes. We know that already. Legally, you can only swap adjacent things. But you can always get any row, any permutation, by a sequence of legal changes. And here's why. If you want a particular arrangement of your numbers 1 up to n, or your bells, you think, okay, what do I want in the final position? If it's not there already, I can just find it and then just swap it with adjacent bells all the way until it's moved into the right place. Then you move on to the next one. If what I want isn't there already, again, I can do this swapping. So that shows you can obtain any permutation with legal changes, just with swaps. It doesn't tell you can do an extent, though, because obviously, how do you know you're not going to get repetitions at some point in that? So let's just look at this hunting, plain hunting. We had, for 4 bells, we had this cross peel A, B, C, D, that was our R, and then S we had B, C, the middle pair. I want H. H will be the set of all permutations, all rows that you can make from these two R and S. So let's see, this is what happens. If you start with rounds, 1, 2, 3, 4, in the bottom corner of that octagon there, then R, I've coloured the edge for R in red, and I've coloured the edge for S in blue. It's S for, it's not really for cyan, but anyway, R is for red. And from 1, 2, 3, 4, you can do S or you can do R. And then you get to some other stuff, and for each one, you can do S or you can do R. So there's only 2 edges coming out of each point. This is a mathematical graph. And you just keep working round, and you get 8 rows. You can't get anything else, because at every point, you've covered what happens with R and with S. So this is the things you can get. It's all you can get, and there's no escape from that set, because any permutation, if you combine any 2 of these things, then you're just making a longer string of R's and S's put together, and so this set itself is closed. It has that closure property that we talked about for groups. So it's a subset of a group that is itself closed. That makes it a subgroup. It's a group in its own right. So it's a subgroup. It's a group. And there are 8 things in it. Now, we want 24 things if we want the whole set of permutations. We've got a third of them here, 8. We saw when we did plain bob minimus that we kind of did our plain hunting. We've got 8 things. And then we shifted it and did it again, and shift and did it again. And this is very similar to the idea of, if you take a line in space, if you translate it, what you get is a parallel line, and that, of course, doesn't touch the original line at any point. The exact same thing happens in groups. If you have a subgroup, and you take something outside of that and shift everything in that subgroup by that amount, what you get is a set which does not intersect the original one in any place. That set is called a coset, sort of a companion set to the original one. So sort of the technical bit there is that if you take some X in your group, and you compose it in turn with everything in the original subgroup, so it's like translating everything by the same amount, then what you get is called a coset, and it's a shift of this original subgroup into something else. It isn't a subgroup anymore, but it's a set in the group that's completely different from what you've got already, disjoint. So let's look at what we did for our plain hunt. We did plain hunting here. E stands for the identity element, not doing anything. So if you start with rounds and don't do anything, that's rounds. Then we did R, and then S, and so on and so on. We get to the final point. We don't do the final S, but instead we do our element, which I've called on the slide T, which is swapping C and D over. That's what we did before. That gives you a shift of your hunting group. It's one of these cosets, and that gives you a completely different set of 8 things. Then you shift it again to get a third coset, and those 3 together give you the whole of S4, the whole set of permutations. They give you an extent. So this is how we can make our group structure appear in bell ringing. This plain bob all along was a compilation of cosets. Well, that's fine. What we've learned from this, not quite there, what we've learned from this is that maybe we can get some structure using our groups with these coset ideas. I just want to show you a prefigure in the next slide. You do see these hunting groups in another context. So on this slide here is a picture of the symmetries of a square. It's actually the same structure mathematically as the hunting group. if you label the vertices A, B, C, and D, you'll see that reflection in a vertical line is exactly swapping A and B, swapping C and D. That's our R. Reflection in a diagonal line swaps B and C and leaves A and D where they are. And there are the other symmetries. There are 8 symmetries of a square. We can say that the hunting group on 4 bells is what we call isomorphic to, the same thing as the group of symmetries of a square. So symmetries of a square form a group. And you can see this in this because it's the hunting group. But importantly, this is one example of where in mathematics we can take things from one context and import them into another context without having to do any extra work. I won't say we're lazy as mathematicians, but we are trying to be efficient. So group theory is one of these amazing areas of maths which allows you, because groups occur so much in mathematics, they occur in geometry, they occur in algebra, they're all over the place in number theory. We've got something that we know about bells, which is you can make everything in the hunting group just out of various combinations of these 2 elements, R and S. So we instantly know, without having to check, that you can make every symmetry of a square just with careful combinations of 2 of the reflections. So you can make any rotation here with 2 reflections combined in sensible ways. So for example, the product of these 2 reflections, if you do vertical line reflection and then diagonal line reflection, will give you a rotation through 90 degrees. This applies more generally, so it's true for n bells and regular n-gons, so where n is an even number. So if you have 6 bells, the hunting group in that case has 12 elements, so does the symmetry group of a regular hexagon, and you can make all of the symmetries of a regular hexagon with careful compositions of just 2 reflections. So that's a nice thing to know. Back to cosets then for a minute. They help us determine truth. Cosets are great. Here's why. I've already said different cosets, if they're different from each other, then they're completely disjoint. Just like 2 parallel lines, if they are different in any way, then they're completely disjoint. You don't have any points in common with a pair of parallel lines unless they coincide and they're the same line all along. So this means when you are trying to check some method that you've produced to make a peel or an extent, and if you've used a subgroup and some cosets, all you need to do reduces the checking to just check the top entry in each column, and if those are all different, then we know that the cosets are different, and therefore you don't have to check any of the other entries. We know that they're disjoint from each other. So this is really useful and saves us a lot of time. And if you imagine checking through, let's see, for 5 bells, you need 120 rows, that's 5 factorial. That's a lot to just check by hand, and it gets worse and worse with 6 and high numbers of bells. So if we have a structure that's good for checking the truth, it's also good for the ringers to learn. So let's tell you what Stedman doubles is. So for Stedman doubles, on 5 bells, you do double swaps. So there is a way, which I won't go into the detail of, but if you take these 3 double swaps, they combine to produce, if you're clever, what's called a plane course of 60 different rows. Now, it turns out these 60 different rows in that plane course, just like with the plane hunting was a subgroup, this plane course of 60 is a subgroup of the set of all permutations on 5 things. It's called A5 usually. It's the even permutations, the ones that you can make with an even number of swaps. That's not the whole thing. There are 120 things. But remember, we've got this coset idea. If you now take anything that isn't an even permutation, like AB, just 1 swap, you will put yourself into a different coset. So you can do this thing AB and then repeat the plane course, and you are guaranteed to get 60 things that you haven't yet seen. Well, 60 plus 60 is 120, so that's it. So you're done. So once you've got the plane course, you've sort of halved your work. You get this plane course, and then you just immediately double it by getting a coset, and you're done. So this is Stedman doubles on 5 bells. Well, what can we do next? Well, this is where we're going to see this old problem. So this is actually a nice picture of ringing out the old year in the belfry of Cripplegate Church, St Giles Cripplegate, which I know it's where, when I went to school, we used to have our end-of-term service in that church. Oliver Cromwell got married there. This is a nice picture of them ringing out the old year and ringing in the new. Stedman triples, then, on 7 bells I want to tell you about in a minute or so. 7 bells, so you can do triples. So he found this way. He took 3 triple swaps, and he found a way to combine them to give a plane course, this time with 84 rows. Now, 7 bells in extent has 5,040 rows, different rows, so we would need, a bit of mental arithmetic, 60 different kind of translations, cosets of this thing to get a full extent. Now, Stedman found a way of doing this. He used a combination of two elements. One of them is a triple swap, and one is a double swap, A, B, C, D. But this A, B, C, D is less desirable because 3 of the bells are just left, I would say left hanging, but they stay in the same place. And we don't want that. We want interesting peals where as many bells are moving as possible. So Stedman would have loved, and he said, I want to find a way where I can just only use triple swaps. He said he thought it was possible, but he couldn't do it himself. And this took a while to solve. It took until 1994, 3 centuries, until this was solved. And it can be done, which is fantastic. It can be done only with triple swaps. It's one of these strange things so there were 2, I wouldn't say rival, but 2 different teams of people found out how to do it within a couple of months of each other. And this has been rung, and it works. So it can be done, but this took 300 years. And to solve it, there's a lot of structure underlying how we solve this kind of problem. What's next in bell ringing? Well, we've come a long way from the bell ringers of medieval times. Computers have been used for really quite a long time. I mean, we think about when did computers come in. This is a picture of the Ferranti Mark I up in Manchester. Not by coincidence, this was used in the 1950s to solve a bell ringing problem. It's one of the first things computers in England were doing, of course. Just to say that this guy standing up here is Alan Turing, who was up in Manchester at the time. I don't know if he did any bell ringing problems, but there were problems done on this Ferranti computer. But you still need human involvement. One thing is, the numbers are so big here, you cannot just use brute force. Even modern computers, you can't just do brute force to try all the possibilities. So you need some intelligence in how you ask the computer what to do, but also you then need to look yourself at what is produced, and does it pass the criterion of being sounding good, of being easier to learn, and all those kind of things that we might want. If you don't have a handy belfry near to you, or you can't get there at the moment because of restrictions, handbells are the way to go. There are lots of online handbell ringing activities you can do. And I would say, though, you will need to practice quite hard to beat the amazing, I have to say, feat in 2007 of 3 members of the Ancient Society of College Youths who rang 100 different extents on 6 handbells. So for 6 handbells, that's 720 rows. So they had to learn those, and then they did 100 different ones, which is pretty amazing, and they did it without stopping. And they were ringing for 24 hours and 9 minutes, which is quite astonishing achievement, just to do it, physically do it, and to learn all that stuff and to not get it wrong. So that's totally amazing. But, perhaps we can start with 4 bells and work up from there. Well, that's all I've got time really for today. Just a shame there's so much more one could say. Thank you very much for listening. If you are a bell ringer, I as a mathematician have a feel for, this is my neck of the woods, group theory and permutation groups. And so I have a feel that for some questions that might be interesting for me to try and solve, but I don't necessarily know that those will be interesting to bell ringers. So if you're a bell ringer, do feel free to get in touch with me and tell me what needs solving in bell ringing. Maybe we can have a talk about that. If you missed any of my other lectures on mathematics and music, you can go and watch those on the Gresham YouTube channel if you would like to. This one will appear there as well in due course. And I just want to briefly plug the next lecture. So for my final 3 lectures of this academic year, we're moving from mathematics and music to mathematics and writing, which is a really fascinating area. I'm so excited about this. So we're going to begin next time with a look at how mathematical ideas have been used in fiction. And it's called Mathematical Journeys into Fictional Worlds. For example, we'll look at the curious Victorian satire, Flatland, which features a 2-dimensional universe where the inhabitants are polygons. And it's a satire on various things that were wrong with Victorian society at the time. We'll also use maths to explore what life would really be like for the giants and the Lilliputians of Gulliver's Travels. Here he is meeting the King of Brobdingnag in that picture. And we'll pop into Hogwarts along our way to visit the giant spiders and ask if we need to be frightened that giant spiders can exist in the real world. So that's on February the 9th at 1 p.m. You can sign up online at Gresham and register to watch that. So thank you very much for watching. It's really great to get feedback and comments from you. I'm standing on my own in a room here at Gresham because of the current COVID restrictions. I really hope that in the future you can meet in person and I can see some of you for real in real life. But for the moment, we will carry on our live streaming, and it's really great to know that people are enjoying these lectures. So thank you very much.